How accurately can we predict the number of primes below 1 million or any number? The answer depends on the Riemann hypothesis. If the hypothesis is true, our prediction is only off by about the kind of error we see in a coin toss. Pretty accurate. All of this conclusion begins with j of x, Riemann's prime counting function. Unlike the smooth Li of x, j of x captures even the finest isolations. Here, the key part is the second term. It adds up the contributions of complex numbers, called non-trivial zeros. It brings Li of x closer to the jagged pi of x, the actual number of primes. A0 row equals beta plus I gamma. The combined effect of all the zeros is on the scale of x to the beta multiplied by log of x. Simply, on the scale of x to the beta as well. We are ready to move to the Riemann hypothesis. The real parts of all non-trivial zeros are exactly 1/2. Beta equals 1/2. So, the combined effect of all the zeros is on the scale of x to the 1/2. It stays close to the root x scale. This scale eventually explains the difference between pi of x and Li of x, the error between the actual number of primes and the estimate given by Li of x. If the Riemann hypothesis is true, pi of x minus Li of x stays close to the square root scale. As x grows larger, the relative error gets smaller. The actual counter primes and Li of x become nearly identical. Li of x converges to pi of x. The number of primes predicted by Li of x does not go too far from the actual number of primes. Primes are not completely random. They are deeply structured. That's the conclusion if the Riemann hypothesis is true. But if the hypothesis is false, then at least one non-trivial zero has a real part greater than 1/2. The overall effect produced by the zeros becomes larger than the root x scale. The error in pi of x minus Li of x can become much larger. Primes would appear to behave far more irregularly and randomly. The convergence of Li of x toward pi of x would also become slower.